This video is sponsored by Let's Get Rusty. This video is about parsing, which is probably the most discussed topic in the context of compilers. Some see it as the most important part of the compiler, because it does the understanding part of the translation process. And often courses mainly focus on parsing and neglect the rest. So there is no way I can do this topic justice in just one short video. But what I can do is give you a theoretical foundation, clarify some terms, and build intuition. Hi, and welcome to Premature Abstraction. This is the third video of a series where you learn all about compilers, one of the oldest and still most important topics in computer science. The goal is that by the end, you'll even be able to write one yourself, so please subscribe if you don't want to miss that. In the last video, we talked about the lexing stage, how the actual characters are transformed into a sequence of tokens. The parser now takes this sequence and transforms it into a tree structure, according to some formal grammar of the language that we want to translate. But before we get into the actual algorithms, we need to clarify two fundamental terms. A context-free grammar is basically a recipe for building valid programs. Instead of checking the code directly, it describes how you could generate every valid token sequence in the language. The grammar has two kinds of symbols. Terminals are the finished pieces, the actual tokens, like we saw them a lot in the last video. Non-terminals are placeholders for bigger chunks of structure, like expression, statement, or program. And then we have the production rules, which tell you how a placeholder can be expanded. An expression can be a term, followed by a plus, followed by another expression. Finally, there is a start symbol, the one top-level placeholder. If you start with expression and keep expanding non-terminals using the rules, you eventually end up with only terminals. That step-by-step expansion is called a derivation. Now, parsing is basically doing this exact process backwards. You're given the terminals, and you reconstruct which expansions must have happened. Oh, and in case you wonder, it's called context-free, because each rule expands a single non-terminal in the same way, no matter where it appears. Expression expands according to the same rules, whether it's inside parentheses, a plus, or anywhere else. The second important term is the syntax tree. There are two common flavors. A concrete syntax tree, CST, also called a parse tree. It reflects the grammar literally and contains all tokens from the input stream. And on the other hand, the abstract syntax tree, AST, a more condensed form that keeps only the meaningful structure. So things like semicolons or braces are dropped after they serve their purpose for building the correct tree. The parse tree is how the grammar recognizes the program, and the AST is the essential structure the compiler actually cares about. With the definitions out of the way, we can finally talk about parsing strategies. There are two big families you'll hear about most of the time: top-down parsing and bottom-up parsing. In both cases, we usually read the input left to right. The difference is in what we're trying to do. In top-down parsing, we start from the grammar start symbol and try to figure out which rules could have produced the input. In bottom-up parsing, we start from the input tokens and build upward until we reach the start symbol. If everything goes well, both produce the same output, but we will soon realize that one of the two is way more powerful than the other one. Let's start with top-down parsing. A very common class here is LL parsing. The name will soon make sense. Let's trace how this works with the grammar from before. Our input is ID plus ID. We start at expression and need to pick a rule. The first token is ID, which matches term, but there are two rules starting with term, so we peek at the second token, it's plus. That tells us to expand expression into term plus expression. Now, term is the leftmost non-terminal. We expand it to ID. That matches the first input token, so we consume it. Then we consume plus, and we are left with one more expression. Again, we peek ahead, no more plus after the next ID, so we pick expression goes to term, expand term to ID, consume it, and we're done. Notice how we always expanded the leftmost non-terminal first. This is why it's called LL. We read the input from left to right, and then construct a leftmost derivation. You can also see a K after that, which stands for how many tokens of look ahead the parser has. Alright, and how do we implement such an algorithm? The most common practical form of top-down parsing, especially in handwritten compilers, is recursive descent parsing. This is popular because it's simple and intuitive. You often can map grammar rules almost one-to-one into functions which recursively call each other. So if your grammar has non-terminals like expression and term, then your parser code may literally have functions with those names. That makes it very nice to read and maintain. And it also makes it easy to mix parsing with custom logic like special error handling. The nice thing here is that the program's call stack acts as the parser stack. Recursive descent uses the normal function call mechanism to remember where it is. And if you don't want recursion, you can implement the same logic iteratively with an explicit stack. And this may be important, because if you remember the first video of this series, we may still be in the bootstrapping phase of our compiler, where we don't support recursion yet. But top-down parsing has an important limitation. A classic LL parser cannot handle left recursive grammars. For example, our grammar writes expression goes to term plus expression. That's right recursive and it works fine. But if we had written it the other way around, expression goes to expression plus terms, that's left recursive because the non-terminal starts with itself. If you implement that directly in recursive descent, the parser function calls itself immediately and never consumes any input, so you get infinite recursion. Luckily, left recursion can always be eliminated by rephrasing the grammar. The other strategy is bottom-up. The big family here is LR parsing. Let's trace the same example bottom-up, ID plus ID. This time we start with the tokens and work upward. We read ID and recognize it as a term. We could try to reduce term to expression, but then we'd be stuck with expression plus ID and no matching rule. So instead the parser tries to keep going. It adds plus, then reads the next ID and reduces that to term. Now term itself can become expression. And finally, term plus expression matches our first rule, so we reduce the whole thing to expression, and we're done. Now you may wonder, why is it called LR? Surely the R stands for rightmost derivation, but it's not obvious that this fits. The key is that it's rightmost derivation in reverse, like this. What we just traced by hand is essentially what our shift-reduce parser does mechanically. It has two core actions: shift, read the next token and push it onto a stack, and reduce, when the top of the stack matches the right-hand side of a rule, replace it with the left-hand side. So the parser repeatedly decides, do I shift one more token or do I reduce what I already have? Over time, small pieces become bigger pieces, until the whole input reduces to the start symbol. LR parsers are usually not written by hand, but generated. Not going too much into detail here, but this is because implementing them involves writing big parser tables, even for medium grammars, so the parser can anticipate which action is valid next, considering also what is already on the stack. Now, given the symmetry of the two, it may be surprising that LR parsers are more powerful than LL parsers. The intuition is that LL parsers often need to make decisions early, when expanding a non-terminal. LR parsers can delay decisions before committing to a specific parse. They keep reading and use more context from what has already been seen before deciding on how to reduce. Because of that, LR parsers can handle a strictly larger class of grammars than LL parsers. A central term when talking about parsers is ambiguity. A grammar is ambiguous if the same input can be parsed in more than one valid way. In other words, if multiple parse trees match the same token sequence. Sometimes ambiguity is intentionally tolerated and resolved with extra rules, but often it's something you want to avoid. The classic example is the dangling else problem. If you write nested ifs and then an else, the question is, which if does the else belong to? Most languages use a disambiguating rule that says the else matches the closest unmatched if. You can encode that directly into the grammar, but in practice it is often handled via parser rules or disambiguation conventions, instead of making the grammar more complicated. The important point is, the grammar alone may allow multiple parsers, so language implementations need a way to choose the intended one. Operator precedence is another example of disambiguation. Say we want to add multiplication to our grammar. If we naively write expression goes to expression plus expression, or expression times expression, or ID, then the input ID plus ID times ID is ambiguous. Two different parsers are valid. We want multiplication to bind tighter. One way to enforce this is to add a layer to the grammar. We add this non-terminal called factor with the following rules. Because multiplication can only appear inside a term, and term is always nested within an expression, this new structure means that multiplication binds tighter than addition. The other way is to keep the grammar simpler and use precedence and associativity declarations or dedicated parser logic. So when people say, in a compiler operator precedence is part of parsing, this is what they mean. Now before we dive into what real languages actually use, let me take a moment to talk about this video's sponsor, Let's Get Rusty. If you're a developer, you probably heard Rust mentioned a lot lately. And for good reason. Companies like AWS, Microsoft and Google have been heavily investing in Rust for performance and safety critical code. So if you want to get paid to build fast, reliable software, whether that's backend infrastructure, robotics or even blockchain, Rust is a great language to have in your toolkit. Let's Get Rusty offers Rust training for individuals and teams, with a big focus on practical skills and helping people move into Rust roles. They have already helped thousands of devs master Rust, and the best part is that they've got a new cohort starting next month already, and spots are limited. So if you're curious, check out letsgetrusty.com, start with abstraction, or click the link in the pinned comment below this video. Now, let's compare handwritten parsers and parser generators a bit more directly. There are many advantages when writing the parser manually. Good error recovery and diagnostics, because you can tailor everything. Flexible combination of parsing and actions. Easy to integrate parser behavior and the rest of the compiler codebase. At the same time, generating a parser also has its merits. It can save a lot of work on initial generation and then when maintaining later. It has a strong theoretical foundation, and it's great when the grammar is already well specified, which improves correctness in comparison to manually writing ones. So there is no universal winner here. A lot of compiler engineering is choosing where you want flexibility and where you want automation. So what do real programming languages use? The answer depends on which compiler we're looking at. Many compilers use handwritten recursive descent parsers because they are easy to control and very flexible, especially for diagnostics and special cases. Examples would be Java with OpenJDK, Rust, C++ with Clang, JavaScript with V8 or Go. Many others use parser generators, often with LR family parsers, because they can save a lot of work and support a broader class of grammars. For example, OCaml, Haskell or PHP. And of course there are also other parser strategies as well, for example Python switch to PEG parsing. So, as always, the parser strategy is not just a theoretical choice, it's more an engineering trade-off. Error handling is often an afterthought in software engineering. However, when it comes to compilers, it is one of the most important parts, as the compiler is the translator between human and the machine. And when the human makes a mistake, the compiler should help and not just complain. This is one reason why error messages are such a big deal in modern language tooling. In fact, for some languages, people actively cite compiler diagnostics as a language feature, such as Rust. A practical issue is that the parser often notices an error later than where it was actually introduced, as it tries to make the best out of the given input. You remove one brace, and now the entire file turns red. That doesn't mean that the whole file is wrong, but the parser lost track of structure. Also, many programming languages were not designed with parser error recovery in mind, which makes the job even harder. A nice counterexample is Ada, which was designed from the ground up to be unambiguous. So the parser can insert virtual nodes into the code, so it can continue parsing and report more useful follow-up errors. LR parsers also have a useful property called the viable prefix property. They detect an error as soon as the current prefix of the input can no longer be part of any valid parse. That's one of the reasons why they are attractive in practice. But in general, there are 4 classic error recovery strategies you should know, and in practice compilers often mix them. First, we have panic mode recovery. This is the simplest one. When an error is detected, the parser discards upcoming tokens until it finds a synchronizing token like a semicolon or a closing brace. The advantages are that it's simple and robust and easy to implement. Also, there is low risk of infinite loops. The downside is that it may throw away a lot of tokens and miss some useful context. Next, there is phrase level recovery. Here, the parser performs local corrections that let it continue. For example, insert a missing semicolon, replace a comma with a semicolon, or delete an unexpected token. This can produce very nice diagnostics, but it needs care. If implemented poorly, it can loop or create misleading cascades. Also, the real error might be earlier than the point where the parser finally notices something is wrong. There is also error productions. Here we extend the grammar with rules for common mistakes, so the parser can recognize known bad patterns and produce targeted messages. This can be very user-friendly, but it makes the grammar bigger and more specialized. Of course, it can also be hard to anticipate what kind of mistakes programmers will make in the first place. And last we have global correction. This is the theoretically fancy one. The parser tries to find the closest valid program according to some cost function, for example the smallest number of insertions, deletions or substitutions. This sounds great, but it can be computationally expensive. And even if it finds the closest valid program, that may not be what the programmer actually intended. So it's elegant in theory, but often limited in practice. At this point it's useful to zoom out a bit. Why do we need grammars at all? Why not just use regular expressions for everything? The short answer is that grammars are more expressive. Context-free languages are a superset of regular languages, in the sense that every regular language can be described by a CFG, but not every context-free language can be described by a regex. A classic example is the language with equal numbers of a's followed by b's, so a to the n, b to the n. Regular languages cannot express that, because they cannot count and compare like that. A more programming language relevant example is matching nested brackets. Nested structure is exactly where CFGs shine. Now, if CFGs are more powerful, why do we still need regexes in the lexer? Because splitting and lexing and parsing is elegant and practical. Lexical rules are often simple, think of identifiers or numbers. For those, regexes are easier to write, easier to understand, and lexer generators can make very efficient scanners from them. Then the parser focuses on the nested structural part of the language. And another point about formal languages in general. Context-free grammars can describe structure, but they cannot describe all the rules of a programming language. For example, a CFG cannot generally enforce things like a variable must be declared before use, or a function call must have the right number of arguments, or a variable must be mutable before assigning to it, or that all types must match. Those checks belong to a later compiler phase, semantic analysis. This is also where the interplay between lexer, parser and semantic analysis becomes really elegant. The lexer can produce an ID token. The parser can use that token purely structurally, without caring yet which variable it refers to. And semantic analysis later assigns actual meaning to that identifier. So each phase focuses on what it does best. At the end of parsing, what we naturally get is a concrete syntax tree or parse tree. But in practice, many of its nodes exist only because they help the parser recognize the grammar. They are not directly meaningful for later compiler passes. And since the later phases may traverse the tree multiple times, we usually want a more compact representation, the AST. There are two common ways to get it. First would be to parse into a concrete syntax tree and then run a separate parse that transforms it into an AST. The advantage is that the grammar and the parse results stay very explicit and reusable. The disadvantage is that you have to pay for an extra parse. And the second option would be to build the AST directly during parsing. This is common with parser generators, where you attach actions and directives to the grammar rules. The advantage is efficiency, no extra conversion pass. However, a downside is that the grammar specification becomes tied to that AST building purpose, which can make it less reusable for other tools. So again, it's a trade-off between clarity, reuse and efficiency. One more thing before we close. A quick thank you to everyone supporting the channel on Patreon. Your support is what keeps the series going. So from the bottom of my heart, thank you. If you'd like to join, the link is in the description. So yeah, parsing is the point where the compiler stops seeing just tokens and starts seeing structure, which is great, but still only syntax. At this point, the compiler can say, this looks like an if statement, or this looks like a function call. But it still doesn't know whether that function actually exists, whether the arguments match, or whether any of this is semantically valid. And that's what comes next. In the next video, we'll look at semantic analysis, the phase where the compiler starts connecting the structure to actual meaning. That's where names get resolved, rules get checked, and the syntax tree starts becoming something that the compiler can actually reason about. So if parsing is about what shape does this program have, semantic analysis is about, okay, but does it actually make sense? And that's where things get really interesting. This has been Premature Abstraction. Thank you for watching.